thanks everyone. My name is Ben. So just to dispel any confusion, there's two Bens in our lab. I'm not on the lead. Yeah, to add a bit of fuel to that fire, I'm going to be talking about seabed characterization using what I'm calling multi-parameter and multi-source backscatter. So I really am kind of on more the application and the mapping side of things rather than the acoustic side. And so multi-parameter, I'm just referring to the use of angular backscatter to infer seabed characteristics, but also frequency-specific backscatter, and mix the two, so it's frequency, angular, specific backscatter. And then, as we kind of started talking about too, we've got some interest in trying to use not only the frequency information, the differences in depth, but also frequency, angular, depth information to infer substrate properties based on penetration. And then by multi-source, I'm just referring to the use of potentially multiple vessels, echo sounders, in surveys that might only be partially overlapping. So these are kind of two subjects that I see as related in a lot of ways. So I'll be hitting them both a little bit today. So just to start with the multi-parameter multi-beam, obviously backscatter depends on not only the substrate, but also the angle with which it impacts the seabed and the frequency which you're operating. So with the advance of these multi-frequency systems, we're now able to collect a lot more of that information, so frequency and angle over a given area, which increases the amount of inference we could potentially make using that information. So I think there has been like a shift towards trying to retain more of the angular and the frequency information in the literature, like for characterization recently, kind of based on this technology. Like I said, another interest is in trying to use differences in depth as some sort of proxy for substrate penetration and therefore sediment characteristics. So this map on the bottom right is just a simple overlay of different depth surfaces in a multi-band raster between 1 and 200 kilohertz, 1 and 4, 2 and 400. And you can actually see some seabed features that look like they match the backscatter. That's just differences in measured depth. And obviously it's not compensated for anything angular, so you can see quite strong angular artifacts in that. But the way we're looking at using those pieces of information is all predicated on like image-based segmentation methods. So if you're familiar with like the concept of superpixels, it's kind of similar to that. It's segmenting at an extremely high resolution, like to get really small image segments, from which we can aggregate the high resolution angular and frequency information. So even though you know, a given angle and frequency might only impact a small area on the seafloor, we can aggregate it to a slightly larger area using segmentation techniques. But more importantly, it allows us to co-locate measurements from different angles and different frequencies, and that's kind of where it starts to get interesting. So we can aggregate different angles from different frequencies across the whole study area. So for instance, between 10 and 55 degrees and 100, 200, 400 kilohertz. And we can do the same with differences in measured depth at the pixel level, not at the graph, not at the surface level. So differences between 100 and 200 kilohertz, 100, 400, 200, 400, all at different angles. And we can try to co-locate some of those measurements to start to draw inferences of them. So, for example, if we look at neighboring angles of the same frequency and we plot the values that we see at the co-located areas, they're highly related, very correlated, and we can see that those relationships get a bit weaker as we change angle and frequency, and they become nonlinear if we go to more disparate angles or more disparate frequencies. But other relationships that are pretty interesting, if we look at some of the backscatter variables, so like the 200 kilohertz at 10 degrees versus the difference in measured depths at between 100 and 400 kilohertz at 16 degrees. We see a pretty strong negative correlation, which makes a lot of sense because you would expect higher backscatter values to represent higher sediment, therefore no differences in penetration between signals. So we can aggregate all that correlation information into kind of these summary correlation plots. So this just shows on both axes we have backscatter at 100, 200, and 400 kilohertz measurements, and they're increasing at each bin by 10 5 degrees. And so nothing too exciting here. We have decreasing correlations with changes in frequency and angle, but it's a bit more interesting looking at the depth difference measurements. So again, we have depth differences measured between different frequencies, increasing by angle on both axes. So just a couple kind of interesting quick takeaways from looking at that plot is that we only really have strong correlations at angles less than 45 degrees, even with different frequencies. So that's kind of interesting. And there's also kind of this zone, which I think is kind of neat in the 200, 400 kilohertz depth difference measurements, where we have correlation across all angles with the 100, 200 depth difference measurements only at about 40 to 45 degrees. So just kind of interesting. The most interesting of all, I think, is comparing backscatter measurements to the depth difference measurements at different frequencies. So again, we only really see strong correlations at less than 45 degrees for the depth difference measurements, but across the full range of angles, at least somewhere for the backscatter measurements. And then I just want to point out this region, which I find interesting in all of these subplots, which is high or oblique angle backscatter compared to depth difference closer to nadir, and we see correlations across a lot of frequencies, which is really interesting to me. So how to use that information for substrate characterizations is what we're really looking at here. So we can retain kind of all that rich angular frequency data and actually use the correlations to try to fill in the gaps in some ways. If you remember, even after we aggregated those angular soundings across the data set, it wasn't fully continuous. We still had essentially gaps where we didn't have all angles or all frequencies represented. I won't get into the details right now, but using some Markov chain Monte Carlo methods, we can actually simulate what the missing values might be based on those correlations that I just showed with the plots, and get estimates for each angle, each frequency, and each backscatter and depth penetration value across the entire data set. So quite a rich amount of information. And again, we kind of have this high spatial and acoustic resolution, which is what we're really after. And it kind of, again, it's kind of like the superpixel idea, if you're familiar with that. But in summary, it's two different metrics, so the backscatter and the depth difference across 3 frequencies and 16 different angle bins. So it's like 96 different variables, if you want to think of it that way, that we can potentially use to characterize the seabed. And so we can pull out some interesting kind of macro statistics from doing that. For instance, we can choose any one of our segments and look at what our response curves are for backscatter across different angles, or even the depth difference across different angles and different frequencies. And we have estimates of uncertainty too, where we've done some of those simulations to try to estimate the values that we didn't observe. And then just quickly, we can kind of look at from the underwater video that Craig mentioned we collected in the harbor, some differences between observed substrate types with various response curves. And it looks like they're possibly descriptive of those substrates observed in the videos. But what's kind of cool about all this information is some of the quantitative inferences we can make, I think. So we have grab samples, not that many, but some grab samples across the bed basin. So what we've tried to do is stick all the the 96 variables that we extracted from the backscatter, the image information, into a neural network and try to predict a bunch of the grain size parameters in the grab samples using all that information, but a low sample size, a low grab sample size. And we use that to predict like the mean grain size in sediment sorting, for instance, across the basin to a fairly high degree of accuracy. Variance explained scores in like the mid-70s, which isn't too bad for a low sample size. And then just kind of getting at that conversation we just had, it's interesting to think about what we're actually mapping here. If we have different penetration depths, different angles, and everything, you can see that what we think is subsurface features in the 100 kilohertz data is not represented in our predictive maps, and that's essentially because we've only grabbed the surface with our grab samples. We don't have any subsurface samples. So what your machine learning model is learning is only as good as the ground truth data. So if you don't have any subsurface samples, you don't represent them in the output. So it only extracts the useful information, which is kind of the really great part of using such an approach. So now just switch gears a tiny bit. A similar concept, I think, is the use of the multiple surveys, which don't necessarily cover the same extent. So it's usually legacy data where you maybe got multiple vessels over multiple years, multiple sounders, and that's what we see in the Bay of Fundy. It's maybe the motherlode of all multi-source backscatter data sets. I don't know. But there's a lot of issues with trying to use backscatter from data sets like that. Obviously, they're uncalibrated systems. We have different frequencies, there's different data resolutions and scales. It's really kind of a mess. But it is interesting to play around with that data set. We've got everything there and start to look at how you might combine information from disparate data sets. So this is kind of what you might see commonly when you just try to mosaic everything together. It's that nice patchwork of backscatter that doesn't really work out, at least in a quantitative way. But one method we're trying to use to make these a bit more comparable is doing kind of relative calibrations where different data sets overlap. So you can see in red, these are two different data sets, and they've mapped some of the same seabed. So the question is, can we use some of that life survey area to try to do some sort of compensation to make them more comparable? So we can plot the error of those areas that they've each mapped as a function of the backscatter of one of the data sets, and we can actually model the error. So I've just put there like a GLM to the error. But using that model, you can try to apply some sort of correction, usually a linear correction, to one of the data sets to match it up. So it's better than just shifting up by a raw value to try to match them. You're actually modeling the error. So that would be the result, is doing that approach on those two data sets. And we'd always try to look at some sort of validation or comparative statistics or something like that. And just to note, we've put together an R package for messing around with these methods that includes a bunch of different visualization tools and validation tools and stuff like that. So that's on GitHub if anybody's interested in looking at it. But anyways, we can run through the data set and do that approach. One good thing is that it's unbiased. I mean, it's statistically unbiased. So if you're just using either like an intercept-only linear model or GLM, it's going to be unbiased in all cases. And it also has the effect of rescaling data. So legacy data, maybe that weren't on any sort of meaningful scale, it would be 0 to 5 values or something. The model will rescale those to the range of the other data set, which can be quite useful. Limitations. Obviously, we're assuming that all of these data sets have actually, they actually have backscatter measurements that represent the same substrate properties, which is a pretty big assumption if you've got different frequencies and different buses and all this stuff that could actually map in different seabed properties. So we really need to ground truth a big map like that, and that's what we've tried to do a little bit. So we have a bunch of videos from the BSWG, and we've identified 7 substrate classes. So we have a backscatter of those classes between different data sets, like before and after we tried to harmonize them. So this is just an example of one of the substrate types before and after. We've done some harmonization from all the different vessels that have mapped it. We can run some multi-parallel simulations and try to determine are the differences between different substrate types significant between data sets or not. What we found was that originally, before any sort of harmonization, we had many significant differences between different substrate types mapped by different surveys. And after harmonization, using that approach, we didn't actually see any significant differences between substrate types. So it's just a bit of ground truth that maybe makes us think it worked a bit at matching up these disparate backscatter data sets, but we can look at a bit of higher resolution information too. So we do have a bunch of legacy graph samples as well. I know it's like stacking legacy data on legacy data, but it's still pretty informative. You can see we look at the proportion of gravel versus backscatter. There is a relationship. It's highly variable. There's a lot of variance in that fitted line right there. But now that we've kind of done this harmonization step, it allows us to do some other interesting exploratory analyses anyways. For instance, we could try more of like a mixed modeling methodology, fit the survey as like a random effect and try to pick out any of that residual variance between gravel samples in what backscatter was for these data sets, and try to see if that error is due to random variability, if it's due to the samples, or if it's due to something intrinsic within each data set. So that's kind of interesting. We see that they do, it seems like our mixed model here with the survey as a random effect picks up a lot of the inter-survey differences and might actually reduce the variance of the model quite a bit. So that's a pretty interesting idea. And then the cool thing is we could actually use a mixed model like that. We could flip it around and repredict onto our backscatter map and essentially try to recalibrate it using the graph samples. Like if we have quantitative measurements, we could try to predict back on those and use the graph samples to partially correct the backscatter. And of course, in that case, your final backscatter map is only going to be as good as the graph samples. Like if you had graph samples that were more noisy than the original backscatter, you're actually making that worse. So it's you have to take that with a grain of salt and really think hard about what you're doing. But it is, I think, a pretty interesting idea for trying to use legacy data that you can't go back and do preliminary calibrations and stuff. So this is just a summary of those two kind of different points, but yeah, looking at using frequency angular parameters for characterization, both backscatter and proxies for substrate penetration to characterize the seabed, and then trying to retain like a high both spatial and angular resolution in the predictions, which I think is kind of an ideal environment for machine learning, where we're just trying to extract the relevant information from a large number of predictors and use it to characterize the passive seabed. And then talk a bit about trying to use data from multiple legacy surveys, doing a bit of relative correction if we can, if they've mapped overlapping patches of seabed, and then potentially ground truthing those corrections and maybe looking at some statistical mixed models to try to correct any residual error that might be intrinsic to the data set rather than the methodology of randomness for the samplings. So that's it.